Today we're taking a look at systems of equations. Now, a system of equations are simply more than one equation that are joined by the word and. So, for example, we'll have a big squiggly bracket out here, and we might have the system that reads like this: y is equal to 4x minus 3, and y is equal to negative 1/2 x plus 7. This would be considered a system of equations. Now, the solution set to the system of equations is simply their overlapping. Or, in other words, when we have two lines, it is their intersection point. So we are going to graph these two lines on the coordinate plane and look for their intersection, and where they intersect, that ordered pair will be considered the solution to that system. All right, let's take a look at example 1. Jerry graphs the following systems of equations using his graphing calculator. Below are the graphs and the table. Can you identify the solutions? So here we have y1 equals 1x minus 2. That is this line that slopes up here and to the right. And then we have negative 1/2 x plus 4, and that's the one here that slopes down and to the right. Their intersection point occurs right here. Now, to find its coordinate exactly, there are techniques we can use on our graphing calculator to get that, or we can also look at the table. We are looking for the x coordinate that has the same y coordinate. And you can see right here, x is 4, y is 2 for both of those. So the point 4, 2, or the ordered pair 4, 2, exists on both of these graphs here. That is their point of intersection. And we say that that is the solution to this system. All right, let's try one for ourselves here. Let's graph this system by hand and find its solution. The first one here, we have 1/2 x plus 2. Our y-intercept is 2, and its slope is rise 1 and run 2. So we will graph a handful of points here and connect that with as straight a line as we can as we slope up into the right through those points. And our next one is y equals negative 3/2 x minus 2. So we have a y-intercept here of negative 3, and this will have a slope of down 3 and run 2. Or we can go back 2 and up 3, and we see that that's going to be our point of intersection there. One more point to graph. There we go. All right, so let's connect these points. And we see that the intersection point here occurs at the coordinate negative 2 over and 1 up. So that is the point that exists on both of those two lines. So we'd say the solution to this system of equations is negative 2, 1. All right, in our next example, we again have a system of equations, but this time we're going to look for the solution by looking at the table. Now, a couple of different things we can do. We can go ahead and graph this in our graphing calculator and go to our table, or we can figure these out here by hand. When I substitute negative 1 in for y sub 1, I'll have negative 7 minus 3, and that's negative 10. Now recall my slope is positive 7, so I'm just going to keep going up each term here by positive 7. So this next one will be 3, and then 4, and then 11, 18, 25, and finally 32. All right, for y sub 2, I'm going to substitute my negative 1 in for my x. 6 times negative 1 is negative 6, plus 2 is negative 4. Now, again, this is going to have a constant slope or rate of change of 6, so we'll keep adding 6, and we'll go in increments of 6. So we'll end up with these points here. And you can see here that the one coordinate that they have in common here is the coordinate 5, 32. So we say the solution to this system is the ordered pair 5, 32. In example 3, we see that Fred wants to enclose a 400 square meter rectangular garden with 70 meters of fencing. Now, in order to do this, it says he's going to use the side of his barn as one of the dimensions of his rectangular garden. So we're going to draw an aerial view here. Here's his barn, and let's say this is his garden coming off the side of that barn. We don't know what the dimensions are, so we're going to label them x and y, and we know on the other side here will be x as well. Now, we don't need to label this side because that's the barn, and that won't consist of any fencing. So the perimeter all the way around is the addition of the two x's plus the y, and I know that that perimeter must add up to equal 70 meters. I also know that the area of this barn needs to be x times y, and that needs to be 400 square meters. So in order to find the xy ordered pair here that meets these requirements, I'm looking for the solution to this system. So to find the solution, I'm going to graph both of these equations on my graphing calculator and find their points of intersection. I've gone ahead and done that in Desmos, and you can see here that the blue line is the equation x times y equals 400, that's the area equation, and 2x plus y equals 70. There's my red line, that linear graph there, and I can see that the points of intersection are 7, 55, or 27, 14. So this gives me the two options for my garden dimensions. I'm going to go ahead and say that x can either equal approximately 7, and therefore y was approximately 55, or x could have equaled 14, while y was equal to, I better go back and check it. I'm sorry, x is 27 and y is 14. So give me my box back here. Hello. There we go. Or x was 27 while y was 14. So those are my two options in order to meet this system of equations. In our next example, we're asked to use our graphing calculator or Desmos to find the solution to this system of equations. So let's get practice using our graphing calculator and show you how you can find the intersection point using it. We're going to enter in our two equations, but first we need to solve for y. So in this first one, we need to divide x over to the other side. So we have the equation 20 divided by x. For our next equation, we need to get y by itself by adding y over to the right side and moving 1 over to the left. So that equation is x minus 1. Now we have our two systems. We can go check out our graph. We see we have a graph of a hyperbola, which is the 20 over x, and there's our linear graph, x minus 1. All right, now we want to find the intersection point. So you can see here that this solution has this system has two solutions. So let's show you how you can find those intersection points. We're going to press second function, calc, and this is going to take us to the calculate menu and go down to number 5, which says intersect. This will allow us to find the intersection point. Now, you can see here that it's asking us for a little bit of input. It says first curve, and it gives us the value of 20 over x. So while we're on 20 over x, we are going to start cursoring to the right, and you'll see that our little cursor is going to come down our hyperbola. We're going to get that as close as we can to our intersection point, and then we're going to press enter. Next, it's going to say second curve, and it's going to jump over to the other curve, and its cursor should be pretty close. So we're going to go ahead and press enter again while it's on that second curve, or this line. And now the third thing that it's looking for is for you to guess. So as long as you put the cursor somewhere close and press enter again, it's going to give you the exact intersection point of 5, 4. So there's one intersection point. Now let's go ahead and do that same thing again. Hit second function calc. Let's come down to intersect. And now, while we're on our first curve, we are going to go all the way over here to the other side, and you'll notice that it started to jump over, and now here it comes up on the left side of that, or the left branch in quadrant 3. We'll get our cursor close, we'll press enter, and the second curve, you'll notice that it now jumps to the linear equation. You can press enter again, and guess, let's just put our cursor close to that and press enter again, and you see now that we have -4, -5. So our two solutions were 5, 4 and -4, -5. In our final example, we're again asked to use our graphing calculator or Desmos to solve this system. So again, we're going to graph these two linear equations this time and find out how many solutions there are by looking for the intersection points. So I've gone ahead and done this, and you should try it too using your graphing calculator or Desmos. But here's what the graphs look like on Desmos, and you can see here, as we zoom in, these lines appear to have the same slope. In fact, they do have the same slope, and therefore will never intersect. Well, these are parallel lines, and because the lines will never meet, they will actually have no solutions to this system of equations. So we'll say that this solution is the empty set, or no solution.